So in this lesson, I want to remind you about what it means to describe an acid as either strong or weak. And the mistake that many make is that they tend to believe that the strength of an acid is related to its concentration, and that just is not the case. So let me give you an example of that. For instance, it is plausible for me to have two acids of the same concentration. So let's say, this one here on the left, it has a 0.10 mole per liter concentration. And so does the one on the right here, 0.10 moles per liter. Right? But it just so happens that the one on the, I'm going to designate that the one on the left is weak, and the acid on the right is strong. And so in this case, we can't really go by concentration because they have identical concentrations. So what does it really mean for an acid to be weak or to be strong? Well, it has to do with the degree to which that acid can dissociate in water. Now, conversely, another scenario I might have is that I might have, for instance, two acids, one where the concentration is, let's say, for instance, 0.50 moles per liter, and one where I have a concentration of 0.050 moles per liter. And I'm not going to do anything to change my labels of weak versus strong, because again, even though this solution on the right is more dilute, it doesn't necessarily mean that it is a weaker acid. Let me talk a little bit more about this in the next slide. So when we talk about strong acids and bases, we're talking about acids and bases that essentially dissociate 100% in solution. So for instance, if I were to isolate 100 particles of HCl, hydrogen chloride or hydrochloric acid, and dissolve them in water, then I would expect to see 100 molecules or 100 ions of hydrogen and 100 ions of chloride present in solution. All of it would go into solution. And the same would hold true for a base that was a strong base. 100% of its ions, or close to 100%, would dissociate in solution. So what does it really mean? It means that we're talking about a situation where these reactions are essentially going to completion. So these reactions are happening 100%. There's no reverse reaction. This is not an equilibrium system. Let's take a look at what it means for an acid or base to be weak. So weak acids and bases, we would say instead, don't dissociate 100%. Rather, they reach an equilibrium. So there's an equilibrium that eventually gets established between the original acid molecules and their dissociated or ionized ions. So only a small percentage of them will dissociate, and the rest will just remain present in solution. That's an important distinction, right? So we're not really talking about concentration. We're talking about the degree of dissociation. And again, these are just made up numbers. Perhaps they're true at a given temperature, but it's meant merely for illustrative purposes. So the fact that I'm only going to have a certain number of these of my weak acids or bases dissociate means that there's a point where the equilibrium is reached and the reaction happens in the reverse direction. Okay, so we would say that this system reaches what we call a dynamic equilibrium. And for every particle, acid or base particle that dissociates, the ions in solution will reform the undissociated particle. So this is why we're even having this conversation about acids and bases to begin with in this section of the unit, is because they do form an equilibrium system that's important to consider. Okay, so as we've seen with just equilibrium constants and then our solubility product constant KSP, there is an equilibrium constant associated with acids and bases, and those we respectively call Ka values and Kb values. And just like our KSP values, we can find the Ka values and Kb values tabulated for us in the back of your textbook for reference. Okay, and so what that's going to allow us to do is to predict whether, the relative strength of acids and bases. So you can see here at the very top that where we see very large values for Ka, and where we see very large values for Ka, what that's indicating to us is that that is a very strong acid. So again, we see these very large values. Oops, not that. That means it's a strong acid. And why does a very large Ka value tell us that the acid is strong? Well, a large Ka value tells us that the products are strongly favored. So for instance, if I go acid, goes on like that, and then I see that my Ka value is large, that means that that acid will dissociate like pretty much completely. In other words, this is not an equilibrium system. If I call this HA, then I would have H plus and A minus present in solution, and there would be 100% dissociation there. So that's a strong, strong acid. Okay, let's keep talking about this. So if I were to ask you, predict whether the following reaction is likely to favor the products or reactants, what we're really looking at is sort of like a tug of war, or actually like a push of war for these acids. And so the way that I would go about this would be to carefully take a look at my Ka values for the two acids that are involved, HCl and HF. And that would allow me to decide. So in the next slide, I have that sort of described for you. So I can see from my chart that the Ka value for HCl is very large. And I can see that the Ka value for HF is smaller relative to that. So what that's telling me is that HCl is like stronger in this sort of push of war. It's going to want to dissociate more readily than the HF is going to be able to dissociate. And what that tells me is that this equilibrium is going to be, as a function of that, pushed towards the left. In other words, my reactants are going to be favored strongly. So let me go through that again. I can see that the Ka value for HCl is very large. That means that HCl is a very strong acid. In fact, it's stronger than HF because HF has a smaller relative Ka value. That means that HCl wants to dissociate more than HF, and it's more powerful at doing that. So it's going to dissociate at a faster rate or to a greater extent than HF is going to be able to do. And so that's going to push this equilibrium towards the left, favoring my reactants in this case. So that's all I have, people. That's it for your quick review on strong acids and weak acids and strong bases and weak bases. I'm going to suggest you do some of the practice problems to help you consolidate these ideas before we move into equilibrium concepts and calculations related to acids and bases.